welcome back. More physics. So, pardon me, I've introduced you now to the concept of work in electrostatics, potential energy in electrostatics, and then I introduced a brand new thing, the electric potential. And I remind you the difference between potential and potential energy is that potential energy is a property that a test charge has as a consequence of experiencing a force, specifically experiencing an electric force caused by the presence of a source charge, the source of that force. Meanwhile, the electric potential, the confusingly named electric potential, is the property of the source charge that gives the test charge its potential energy. So the source charge has potential, the test charge has potential energy. So that's what that is. And so I've talked about work, I've talked about potential energy. The final part of the energy trio is kinetic energy. And along the way, I want to mention the units of electric potential, which are not joules, because electric potential is not energy. It's related to energy, but electric potential is not energy. We'll talk about that. And I thought I would put all these ideas together in the form of an example. So I have in some previous example mentioned the alpha particle. So remember, an alpha particle is the nucleus of a helium atom, and it consists of 2 protons and 2 neutrons. And as before, the 2 neutrons we will ignore because they don't have any electric charge. So here's the problem. We've got an electron in the vicinity of an alpha particle, and it starts out at rest and its initial distance is 10.58 times 10 to the minus 11th meters from the alpha particle. That's kind of a peculiar number, but there's a reason behind it. An alpha particle is, of course, positively charged, has a total charge of 2e. Electron has a charge of negative 1e. So opposite charges attract. The electron is attracted to the alpha particle. The alpha particle has, 8,000 times, roughly, the mass of the electron, so it hardly moves. And so we'll just consider it to be at rest. The electron moves toward the alpha particle, experiencing a force along the way. Work is done on it, change of potential energy, change of kinetic energy. And we're going to make measurements of those things. And the instant that we make our measurements, we find the electron is at 5.29 times 10 to the minus 11 meters. And if you're watching carefully, you'll notice that the initial distance is just exactly twice the final distance. So we can ask some questions about this. First question to ask is calculate the potential difference between the starting point and the ending point. Okay. Now we're going to draw our diagram, but it's probably worth making sure that we understand what question A is asking and what question A is not asking. It's asking the potential difference between these 2 points in space, starting and ending point. What it is not asking it's not asking anything involving the electron. The potential difference is a property only of the source of the force, a property only of the source charge. Okay, and so whatever diagram we create should not involve the electron. So we'll do our diagram. So we have an alpha particle, 2 protons, 2 neutrons. So proton, proton, neutron, neutron. And again, for the reasons I just explained, I'm not going to draw the electron in, not yet. Not for part A. The initial position is, let's say, saving board space. See, it starts out farther away from the alpha particle than it ends up. And the question doesn't explicitly say so, but we'll assume that the electron, or anyway, the 2 points are collinear with the alpha particle. Why wouldn't they be? Right, so the potential difference then is the electric potential calculated here minus the electric potential calculated there. Okay, now this is comparatively new. I mean, I introduced the concept of electric potential in the previous lecture. This is the first time we've applied it, but it's not difficult. The expression I gave you is, well, this is a diagram. So next we'll put a coordinate system on it. We're not going to really need the coordinate system, but it's a good habit. So of the x direction, if you like. Doesn't really matter. We're not going to use it, as it will turn out. But as I say, good habit. Okay, 3. Solve. All right, so not going to involve the electron at all. The potential difference, which is what V is calculated by KQ over R. A couple of things. First off, remember that R is actually R final minus R initial. R is the change of position between the starting location and the ending location. In parts B and C, the starting position and the ending position will be the starting position and the ending position of the electron. But for part A, there is no electron. So it's just the 2 points in space. So that's really why I said it that way. Calculate the potential difference between those 2 places. Okay, so there's that. Q, in this case, is 2 times E, because there's 2 protons. All right, and K, we know what that is. And so we substitute this in, and I'm going to go ahead and put in the numbers 8.99 times 10 to the 9th Newton meters squared per coulomb squared. Q is 2 times 1.602 times 10 to the minus 19th coulombs divided by R final minus R initial, which I could substitute in those numbers, but it's 10.58 minus 5.29, so hopefully you can see that that's 5.29. Well, maybe I better do it. 10.58 minus 5.29 times 10 raised to the minus 11 meters. Ran off the board there. Okay, and I cranked through the numbers, and I came up with negative 54.45 And now let's check out the units. Let's see. I have newtons. I have meters squared in the denominator. I have just meters in the, meters squared in the numerator, just meters to the first power in the denominator. I have coulomb in the numerator, coulomb squared in the denominator. And so I think that's what that is. So that leaves me with newtons times meters, Newton meter divided by coulomb, which a newton times a meter, since we're talking about energy and work and things like that, a newton times a meter is actually a joule. So I'll write that as a joule per coulomb. And that unit, joule per coulomb, is a very common unit that we get a lot. In fact, of course, we get it every time we calculate a potential difference. Sorry, I'm messing with my wires here. So we have defined a special unit for the joule divided by coulomb, for joule per coulomb, and that unit is named after a physicist, of course, as most of these are, and it is named after the Italian physicist Alessandro Volta, and it is called the volt, therefore. The volt is part of the SI system. And it is, and I apologize for this, but it's not really my fault. In fact, it's not my fault at all. The symbol for the volt is capital V. That is to say, 1 volt is defined to be a joule per coulomb. And it is a source of endless despair that the unit for electric potential is the symbol for the unit of electric potential is exactly the same as the symbol for electric potential itself. V for volts, V for electric potential. It's the same letter. Now, when you type it out, like in your textbook or in my lecture notes, what we try to do is when we use V to represent potential, we write it as in italicized. And when we're using V to represent the unit, we use not italicized, just straight up Roman. But the fact is, it's hard to see and it's hard to get used to. All I can tell you is just watch for it, be careful, and eventually you'll get used to it. But in the meantime, it leads to such splendid equations as if I ask you for the potential of the battery in your car, the potential of the battery in your car is 12 volts. Isn't that lovely? Now, the thing is, for me, I see absolutely nothing wrong with that equation. And that's because I have been doing this for mumble-de-mumble years, right? I'm so used to it, I know that just the way this is written, over here, this cannot possibly represent electric potential. This has to be a unit because it's attached to a number. This over here, though, a unit can never be equal to this, not unless you're defining a unit, and here we're clearly not. So this has got to be, just from the context of the equation, this has got to be electric potential. This has got to be volts. And I'm used to that because I've been doing it for so long, but if this is the first time you've seen this, this is bound to be confusing. And all I can tell you is just keep whacking at it. Eventually, you'll become comfortable with it. Eventually, you get used to it. Okay, so there's that. Anyway, so the answer to the question part A is that the potential difference between the 2 points is negative 54.45 volts. Now, the question inevitably comes up, what in the world is that minus sign about? The answer will become clearer after we've done the next two parts, but suffice to say that it represents the effect, let me put it that way, the effect of this electric potential on a positive test charge if you had a positive test charge, which we don't. But if we did, then this minus sign would mean something regarding that positive charge. For now, don't worry about it. We'll just press on. Like I said, after I've done the other two parts, this will make more sense. The next part is, in fact, calculate the change of potential energy of the electron as it moves from the starting point to the ending point. Okay. Now, technically, I didn't need to add the phrase of the electron because potential energy can only refer to the test charge, which in this case is the electron. But I put it there because why not? Well, as I taught you in the previous lecture, the relationship between the potential and the potential energy is simply U is equal to Q times V. Q here is 1.602 times 10 to the minus 19th coulombs. The potential is, oops, hold on, negative 54.45 volts. And evaluating that, I come up with sorry, 1 second. No, leave that off, I guess. Okay, and that gives me negative 8.72 times 10 to the minus 18 joules. Remember, a volt is a joule per coulomb times coulomb. The coulombs divide out, and you're left with joules. Okay. Alternatively, we're calculating a change of potential energy. Potential energy has units of joules, either way. Okay. Notice that the potential energy is negative. The change of potential energy is negative. What that indicates is that the electron lost potential energy in this process, which makes sense. And you may have heard this before. Maybe I've said it before, probably not. This is, let me tell you this now. The electron lost potential energy, and that makes sense because it started out farther from the positively charged alpha particle and got closer to it. But of course, having opposite sign of charge, the force on the electric force on the electron will be attractive towards the alpha particle. And the point that I want to make here is that the electron moving toward the alpha particle happens spontaneously. You don't have to force it to happen. It will automatically happen. If I release the electron, it will immediately start falling towards the alpha particle. I don't have to force that to happen. It happens spontaneously. Now, here's a concept that you can apply in everything in this class, everything in your next physics class, and everything in your chemistry class, any class ever from now on that ever involves energy, potential energy. I'm going to tell you something that you can take to the bank. This will always be true, and it is the following. If a physical event happens spontaneously, then I guarantee you when that event happens, the potential energy of the system decreases. On the other hand, if you have to force something to happen, it won't happen spontaneously, you have to force it to happen, then you are automatically increasing the potential energy of the system. Okay? So anytime you're analyzing a system, just ask yourself, will this happen spontaneously, or do I have to make it happen? If it happens spontaneously, the change of potential energy is negative. You lose potential energy. If you have to force it to happen, you're doing work on the system, therefore you're increasing the potential energy. Always, always, always true. So in this case, since we knew ahead of time that the electron was spontaneously going to fall towards the alpha particle, we knew ahead of time that the answer was going to have to be negative. And so the fact that this is negative does not surprise us. Okay. Notice once again that I didn't put the negative sign in for the charge. The negative sign was already built into the change, the potential difference between those 2 points in space. Okay, cool. Finally, and this won't take me very long, and this is where I finally get around to bringing up kinetic energy. Let's do part C. Which is calculate the electron's speed when it reaches its final position. Easy. Fairly easy. We'll apply conservation of energy. Remember, conservation of energy says that when you do work on something, the work transforms kinetic energy into potential energy, and that the change of kinetic energy plus the change of potential energy has to be zero, or to put it another way, the change of kinetic energy is equal to the negative of the change of potential energy. Now these are the general symbols. Here, I would write this as the final kinetic energy is equal to the negative of the change of the potential energy. Remember, in the context of electrostatics, I tend to drop the delta, but so this U here means it's exactly the same thing as this delta U means up there. It's a change of potential energy. Okay, so, but kinetic energy, frankly, is easy. It's the same, well, first of all, the initial kinetic energy is zero because the electron started at rest. As for the final kinetic energy, there's only one way to calculate kinetic energy, 1/2 mv squared. So that's easy enough. So 1/2 mv squared is equal to the negative of the change of potential energy, which we just calculated, which is minus Q times V, okay? And capital V, don't confuse the velocity with the potential difference. So that gives us that V is equal to negative 2Q capital V over M. M is the mass of the electron. So Q is the charge on the electron. V is the potential difference we calculated in part A, the 54.45, yeah, volts. M is the mass of the electron. Plug in the given values, you can convince yourself that this works. And the answer I got was 4.38 times 10 to the 6th meters per second, which frankly is a respectable speed. That's roughly 1/100th of the speed of light, a little bit more than that. So that ain't bad. Yeah. So this is just conservation of energy. All right, so a lot happened in this example, but the most of it was okay. I mean, kind of a review of concepts that you used in your mechanics class. Really the new stuff that happened in the previous lecture, I had already developed the concept of electric potential. So that's well, I erased it, I guess. But anyway, and then I introduced the unit of electric potential, and so we calculated all that. And then potential energy is related to electric potential. Electric potential is a property of the source charge. Potential energy is a property of the test charge. And then part C was, again, just conservation of energy. So that's that. So the punchline of all of this, I guess, is to show that using energy as a mathematical and physical problem-solving approach is useful, it's easy, it's powerful. But it turns out that electric potential is far more than just a problem-solving technique. It actually gives us some deep insights as to how electric forces, how electric fields all work, and gives us some very powerful tools for handling questions related to those, independent of energy as such. And so in the next few lectures, we're going to talk about electric potential of the source charges in more detail, and we'll see that we can we'll find out some very interesting things in a fairly easy way, easy at least mathematically. So we'll look forward to that. See you next lecture.